Okay, so last time we left off with tautological bundles in the Picard group of the projective space. So let's just recall what is the tautological bundle. So this is a subset of projective space so Z0, Z1, etc., Zn times Cn plus 1. So V0, Vn in Cpn times C n plus 1. And we say it's such that V0, V, so let's just call it V, the vector V, is in C, Z. And it's the tautological bundle in the sense that over every point here, you put the whole line described by that point. Another way to write it, more, let's say, algebraic, is to say that this is the set of all, okay, let's just call them Z's and V's in Cpn times Cn plus 1, such that Zj times Vk is equal to Zk times Vj for every J in K. Yeah, this is the same condition as this, just explicit. And yeah, so they were just recalling this. And so now the projection we usually consider, so usually we consider this projection. Which we call pi 1. The projection onto the first factor, because this gives rise to the tautological bundle indeed. This is the total space of a bundle over Cpn. But we can also consider, let's say, nu, the projection onto the second factor, which we call pi 2. So let's see what this is about. So let's start with the anti-image of 0. So let E be pi 2 inverse of 0. And observe that if you intersect with the anti-image of a point here, so if you consider EP, which is nothing but E intersected the anti-image via the bundle map of a point P in CPN, this is exactly just P and 0. I mean, not P and 0, but P comma 0. So yeah, because the idea here, if you take the anti-image of 0, all these V's are 0, right? So you have basically absolutely no condition on this G, Z, J's, and ZK's, because this is just all 0, so completely free. And in particular, this means that E is bilomorphic to CPN. Yeah? So if you look at the image over 0, you get CPN. But if you look at pi 2 restricted to only to everything but E, the image is of course it's Cn plus 1 minus 0, because it's the image of it. This is a bilomorphism. And why is that? Well, if we're in CPU in Cn plus 1 minus 0, it means at least one of these Vj's is not 0, right? And then these are real equations. So these are equations which are independent of each other with respect to zj. So I mean, you can think like this. If vj is different than 0, then there exists a unique point in CPN such that v is in the bundle, and of course the projection is the correct one. And if you, let's say, if you still don't believe it, we can define the inverse. So map from Cn plus 1 minus 0 into, and of course when I write 0 here, I of course always mean the n tuple, n plus 1 tuple of zeros, into E, descends V to just VV. Yeah, and this is well defined because V is never 0, so this is part of the thing, and of course it satisfies this condition. So basically, you can think of this O minus 1 as just Cn plus 1, but then instead of the 0, you have a copy of CPN. Okay. So to better understand this projection, this pi 2, let's look at it in local charts. So we look at O negative 1 restricted to U0. Okay, so this is just, as usual, the anti-image of U0. And U0 is the usual local chart of CPN where the first coordinate is non-zero. So remember that here we have the local chart phi 0, which goes from indeed this O negative 1 restricted to U0 to Cn plus 1. That sends point Z, comma V into Z1 over Z0, comma, comma, Zn over Z0. So these are the first n coordinates. And then you have to add V0. Okay. And the inverse was this one. So you take V0 inverse of x1 xn, comma, lambda. So maybe I want to write it like this just to remember. You know, this is the chart part, and this is more so the what's it called, the bundle part. And here, to go to the other way, you just have to homogenize this. And here you put lambda times 1 x1 xn. This was the inverse. Okay. So now what happens when we apply, so we think of this as our coordinates. Sorry, this as our coordinates. So what happens when we apply pi 2 to them? So pi 2 of phi 0 inverse of x1 xn comma lambda. Yeah, so instead of we want to look at in the coordinates, so we precompose with phi 0 inverse. Then what you get is nothing but lambda, because projection on the second coordinate is simply this one. So you get lambda, lambda x1, etc., to lambda xn. No? And so phi 0 of E intersected phi 1 inverse of u0. So this is just, you know, the good old O1 restricted to u0. So we want to see what happens to E in these coordinate charts. This is nothing but x1, xn, lambda in Cn plus 1 such that lambda is equal to 0. Okay, because E was the set where the second part is 0. This part is 0, and you see the only way to have this part all 0 is to have lambda equals 0. And this, well, this is nothing but Cn. Because you have x1, xn, and then you have another coordinate, which is just 0. So, going back to us. So, if you look at the whole thing, this is such that if you take the anti-image of a point, which is non-zero, you get simply not really the point back, but basically the point back when you're not 0. Okay. But if you're 0, so P2 inverse of 0 is CPN. And morally, what we're doing is we're replacing the 0 of Cn plus 1 with all possible ways, to approach 0. What does it mean? So you know that CPN, you can think of it as the set of all lines passing through 0 in Cn plus 1, right? So basically here what we're doing, okay, you have your Cn plus 1, and then instead of 0, you put the CPN. And you can think of the CPN by saying that everything that goes through 0, instead of going through 0, goes through a point of CPN, which point? The one which we're coming from in Cn plus 1. And we will see more about that. I mean, we will see this in detail right now. So first of all, let's give a name to all this construction. So the pair O minus 1, comma, by 2. So the total space together with the projection on Cn plus 1 is the blow up of Cn plus 1 at the point 0, 0, 0, 0. And of course, okay, we're saying at the point 0, 0, 0 because 0 is the point which is being replaced with CPN. But you can change coordinates to blow up another point. Okay, you just pre-compose everything with a translation or with whatever you want, and you blow up at a different point. So this construction is not only valid for Cn plus 1, but is valid on every complex manifold. So let M be a complex manifold. And I think now the construction will be even more intuitive. And let P be a point in M. We define M tilde as the blow up of M at P as follows. So first of all, we use this intuition that we're simply replacing the point P with a copy of CPN. And you just say, hey, we just take this joint union. We remove the point and we put a CPN. But then to really say that the CPN is there instead of the point, of course, we have to give an atlas, which somehow reflects this topology. So we give an atlas to make a complex manifold.
Just 1 second. Is M of dimension n or?
Yeah, of course. Yeah, that's
Okay, yeah,
important.
then,
N or n plus one? No, n plus one. N plus one.
yeah, that makes more sense. Yeah, okay.
Okay, yeah. So where n plus one equal dimension. Yeah, that of course is necessary. And here again, we put CPN because, you know, when you're thinking about directions from which you're going to approach P, you can just look it in a chart and then it's like you're in Cn plus one. And this is exactly what we're going to use now to define the atlas. Okay, and we need to make a massive boundary. So, well, of course, we start with an atlas of M. So first, we take an atlas of M, take an atlas of M, such that there is only one chart around P. One chart, U0, such that P is in U0. This is, of course, possible because you take any chart, you just remove a point, and this is still a chart. So you can simply just remove all the P's to all but one. So all the other charts, we just use them, okay? So all other charts, use them for and tilde as well. Yeah, okay, if they don't intersect P, you can just use them on M minus P. Okay. But for F0, U0, for U0, consider phi 0 from this U0 into V. So this is just the chart, right? And we make sure that it's centered at 0, meaning that P, that it's centered at P, meaning that P goes to 0. Okay, this is you can just achieve by translation. So this phi 0 is the chart in M. Okay, so chart in M. Okay. And basically what we do, we make a new chart, which is going to be on U0 minus P union CPN. Because this is what this manifold M tilde looks like on near this place, on near P. So here we put a complex structure. Induced by a bijection. And this bijection, sorry. I can do this. So we go from U0 minus P, union CPN. And we go, where do we go? Well, we want to model this on our Cn plus 1 case. So since this atlas V was in Cn, sorry, this should be Cn plus 1, of course, because we said that the manifold is n plus 1 dimensional. Yeah. So we just model this. So since this V is in Cn plus 1, we just blow up the point 0 in Cn plus 1. So remember, this is the blow up. Okay. And well, if we have a Z, which is in here, you just send it to the corresponding one. So pi2 inverse of phi 0 z. And we know that since z is not p, this is just this point. Okay. But if we are on CPN, then we send this to V0. Okay. So this is a bijection by what we've seen before. Wait, making a mess. I can solve this, I hope. Okay. And now you see that the change of coordinates, so I'm gonna make a new page. The change of coordinates are the same ones, are the same ones we had on M. So this is in fact a complex structure. On M tilde. So remember, by complex structure, we mean a complex atlas, basically. And yeah, so we know that this thing here, it is in fact a complex object. So now you know that near this point P, you have a complex structure, because this is a nice holomorphic atlas, because we're putting precisely this as a complex structure. But then of course you have to verify that the change of coordinates are biholomorphic. And we know that they are simply because all the intersections avoid this point P. And away from this point P, we have just what we had before. Basically, we still have phi 0. Okay. So this gives a complex structure. So now we are gonna understand why blowups are important. And this is very much linked with the fact that you're basically replacing the point 0 with all possible directions to approach this point 0. So maybe to give a little spoiler, this is usually used to desingularize curves, which means that if you have, let's say, a curve that looks like this, like a cusp, if you blow up this point, so this is of course a singular curve, yeah, because it's singular. But these two things are approaching from the same direction. Yeah. So if you do the blow up, this becomes a smooth curve. Blow up to obtain a smooth. So, I mean, that's the idea, but now we'll see it in detail. So what do I mean by this? So we take U in Cn, open, with 0 in U. And we take F, just a function in U. We take S, the hypersurface defined by this F. Be an hypersurface. I guess usually when you speak about surfaces, you think something non-singular, but here we're not asking anything on the gradient of F. So this could be very much singular, and actually we kind of want it to be singular for all of this to be interesting. So the transform of S via the blow up of the point 0 in Cn. We should always stick with Cn plus 1, I guess. No, maybe let's stay with Cn now. The one is S tilde defined. Maybe I'll go here. S tilde as pi2 inverse of S minus 0. So if I just take this, we know that if you remove the 0, the blow up doesn't do anything. It's a biolomorphism. So we don't really care. You know what happens outside the 0 is just a biolomorphism. But if we take the closure, then we're adding something in the CPN. Okay. And I think the best way to look at this is look as an example. So we take S to be ZW in C2 such that Z third minus W squared is equal to 0. The subset of C2. So our function here is simply Z third minus W squared. So this is a singular curve. In C2. And we will show that S tilde is not singular. Okay. So to do these kind of things, you always have to look at charts. And on O minus 1, we have exactly two charts. Two charts. One is the anti-image of U0 via the bundle projection, yeah? And phi 0 tilde. And then you have the other one. So U1. Phi 1 tilde. Tilde is to say that these are the charts on O minus 1, because we used phi 0 to mean the charts of CPN. While on O minus 1, we use phi 0 tilde and phi 1 tilde. And maybe let's just write it down once more. So we have phi 0 tilde negative 1 from C2 into pi 1 inverse of U0. So yeah, let's look at the inverse because sometimes it's more helpful. So we have x0 lambda. This goes to 1 x0, comma lambda times 1 x0. So lambda times lambda x0. So this is what we've seen before, yeah? So if you let me abuse notation, meaning that I forget this trivialization, I'm just going to write pi 2 of x0 lambda 0 to be lambda 0 comma lambda 0 x0. And remember here we're abusing notation. Because, you know, pi 2 is defined really here, not on C2, but if we kind of forget this phi 0 tilde, all good. Okay. Okay, so now let's look what happens to S tilde under this map phi 0. So phi 0 tilde applied to S tilde, but we have, of course, to intersect with our chart because phi 0 tilde is only defined on U0. Yeah. We're simply applying the map. So this is all lambda 0, x0 in C2. Sorry, maybe I should stick with the same order as before. X0 lambda 0 in C2, such that lambda 0 third minus lambda 0 squared x0 squared equals 0. So why is this? Well, because here we had z to the third minus w squared, and you see that our z now is lambda, and our w is lambda squared, is lambda x0, lambda 0 x0. Okay, so when we transform, we get exactly this. Now, if lambda is non-zero, so a point x0 lambda 0, so which is outside of this E, which is called the exceptional set. And again, here we have to intersect. Well, now I'm taking it separate in the sense, okay, this is the chart, and this is what is happening in O minus 1. And maybe I want to recall what's happening downstairs, so what's happening in C2. So I'm just going to write it like this, S minus 0. Yeah. So a point is in here if and only if lambda 0 minus x0 squared is equal to 0. So this is because we're excluding the possibility that lambda is equal to 0. Okay. Yeah, because this E, because phi 0 of E intersected this chart is precisely lambda 0 equals 0. Yeah. So we're simply removing the possibility that lambda 0 is equal to 0. Okay. So now we have this object in this local chart in phi 1. So this looks like C2, right? This phi 1 inverse of U0 is basically C2 with coordinates lambda and x. So we take the closure. So taking the closure. So this is what is happening outside of this E, right? That's the important part. But now if we take the closure of this equation, so think of this as an equation on C2 minus a point, right? And if you take the closure, well, you're just saying, okay, it's just this equation everywhere. So this is simply lambda 0 minus x0 squared. And this is a non-singular curve, right? Because it's just a graph. Non-singular. Okay. Of course, so this is for one chart. This is for pi 1 inverse of U0, but we also have to look at pi 1 inverse of U1, which is the other map, which is the one that goes again from C2, pi 1 inverse of U1, and it sends x1 lambda 1 to the same but switched. So x1 1 comma lambda 1 x1 comma x1. Yeah. So now we do the same thing as before, and we just look at, so phi tilde minus 1 1, and we skip this part where we really show what happens outside of the exceptional set. And we just look directly what happens when you close, but the procedure is the same. So this is simply lambda 1 x1 minus 1 equals 0. So why is this? Remember the equation was z third minus w squared equals 0. So here we're replaced with, maybe I'll find some different color, because this you can think of lambda 1 x1 third minus x1 squared equals 0. So this looks weird, right? Oh, of course, because this is not x1. This should be lambda. This should be lambda. My bad. Sorry. Lambda 1. And so this is lambda 1, and we're all happy. Okay, you should have a third as well. Okay, that's it. Yeah, because here again, we're basically assuming that, so if we look outside of the exceptional divisor, so not at S tilde, but just simply outside, so this thing here, but we won, so S tilde minus E, you have this equation. But on minus E, you know the lambda 1 is not 0. So this is the actual equation, right? Because you can divide by lambda 1. So this is the equation outside of the exceptional divisor, but then when you take the closure, just like we did here, you simply get this equation everywhere. But actually it doesn't really matter what the equation is, because this actually does not intersect E at all. Because you can never have that these are zeros. Like here you do have that this goes through E, because 0, 0 is a point here, but this simply doesn't intersect E. So it does not intersect E. So like the only part, the only desingularization that we did happened on the other chart. So S tilde is a regular curve. Okay, simply because the only point where it could have been non-singular 0, 0, and then we looked at what happens over 0, 0 when we did the closure of everything which is not in 0, 0, and we have two possibilities: what happened in U1, what happened in U0. In U1, simply nothing goes through 0, 0. So we have a bilomorphism, and we're happy because the only singular point was there. While here we did have something, but this thing is not singular anymore. So if you're in every chart, you're non-singular, then you're non-singular. Okay. So this is what we see in the local charts. Yeah, we have these two local charts. U1, okay, pi 1 inverse of U0, pi 1 inverse of U1. But let's really look at it in the blow up. So let's look at it in O minus 1. Yeah, really above. So on this chart, pi 1 inverse U0, S tilde, which we know it's, what was it, lambda minus x0, the opposite, lambda minus x0 squared, lambda 0 minus x0 squared, is parametrized. So I want to look at the parametrization. Parametrized simply by t goes to, what we're using, lambda or x first? We were using x lambda. So it's parameterized by x comma, sorry, by t squared. This is x0 and this is lambda 0. Okay, this is simply a parameterization of this curve in situ. Okay. So now we apply the chart. So phi 0 tilde inverse. Yeah, because this is in C2 and we want to go back to a 1. And we get, so instead of sending t to this, you send it to phi 0 tilde, inverse of t squared. And this we know how it works. You have to send it to t squared, but this is, since this is homogeneous coordinates, this is nothing but 1t. And here you have to, the first one is lambda 0, but the second one is lambda 0 x 0, so t third. So maybe if you don't remember, let's just look again at what phi 0 inverse did, phi 0 tilde inverse did before. Yeah, here. So you send x0 lambda to 1 comma x0, comma lambda x0, which is exactly what we did here. Yeah, 1 comma x0, and then lambda comma lambda x0. So this is the parameterization of this curve on the all one. So this is just a point of O minus 1. And you see now when, so before we were only looking at this basically on this component here. When you have the curve z cubed, where is it? Yeah, z cubed minus w squared equals 0. This is your parameterization, the second part. And what we're adding here is what happens when we reach 0, 0. You see, when you reach 0, 0, you're simply adding this point 1, this homogeneous point 1, 0, which makes sure that everything is non-singular. Okay. And so, yeah, this is what I was saying before. So now maybe let's do it a bit better. So if you just look, okay, this is, of course, it's all complex. So this is what, a two-dimensional, real two-dimensional object in a four-dimensional thing. So oof, who knows? But let's just look at the real parts. So if you look at the real part of that, you see that when you approach 0, 0, the derivative, of course, approaches 0, 0 as well. But the homogeneous part of the derivative is precisely this 1t. Sorry, not of the derivative, of the curve itself. So what we're saying is that we're approaching through this 1, 0 direction, which is precisely this vertical one. Yeah, y equals 0. Yeah, exactly. No, maybe it's the other one. Sorry, maybe should have been. Well, let's just swap w and z. Yeah. So let's say this is w and this is z. So 1, 0 represents this direction. Yeah, the w direction is 0. But remember that, I mean, this now looks, remember that when we are in the complex numbers, directions are like in both sides, right? Because we don't have a good order in C. So it doesn't matter if you like, okay, because this is like, again, this is a real picture. So this might look like it's more like 1, 0. Well, this is more like negative 1, 0. But when we're there in complex projective space, this doesn't matter. And yeah, basically, we're seeing this point, instead of being just 0, 0, becomes 1, 0, 0, 0. No? And everything works fine. Like you can think, you know, this is a branch and this is the other branch, but they glue well together because they approach from the same direction. Okay. So I think all of this is, I mean, blow-ups, I would say they're pretty hard. Because it's a weird construction somehow. But what the really important is in fact to desingularize curve and so compute these transforms. So I think a really good exercise here is to determine these transforms for just a few of them. So you could have z equal a w squared where A is just a complex number. You could take Z squared equal W third. And this, I hope you already have an idea of what should happen. And here we take Z squared equal W squared. It's a bit more interesting because they're the same degree. Okay. So yeah, just try to determine this and observe. I mean, let's just to give a look at the differences here, like why this tree in particular. Well, this is non-singular, first of all. Right, this is just a graph. No matter what A is, this is a graph, it's non-singular. So by our intuition here, you should get something which is really polymorphic to S. You should really get the same thing. Here, it's basically what we're already done. You're just switching the coordinates. But you have two things of different degrees, right? And here, which is really maybe the new case, which we don't really know what's going to happen, you have two things of the same degree. Okay, so this is probably the most interesting one. Okay, so this concludes chapter 2. And now it's time to start with chapter 3, which is perhaps the start of really something new. Because remember, chapter 1 was mostly about recalling things. Chapter 2, we developed this whole notion of bundles, pullbacks, quotients, summing vector bundles, and we concluded with this very nice thing of tautological bundles over projective space. The next chapter, it's all about the RAM cohomology, which I know you know already. But we're going to see it from a slightly different point of view, which is going to be very helpful for chapter 4, which is going to be about abstract the RAM cohomology, and in particular about check cohomology. So as the beginning of every chapter, we will start with recall. So, chapter 3, recalling a few notions. Okay. So now let's start with the definition of vector field. So I'm gonna go very fast through all of this, not much explanation, just write everything. So a section of a smooth section of the tangent bundle of M over U is a vector field. Over here. And you can observe that this set of all vector fields over a particular open set is a module respect to the ring of smooth functions here. Meaning that if you have a vector field and you multiply it by a smooth function, this is still a vector field. Okay. So vector fields are probably introduced to you as derivations, not a section of a bundle. So let's see the connection. So let's take a function. Let's take a vector field. Then the map sends U to R. Let's take a point X and sends it to the vector field applied to F at the point X. Yeah. This is a smooth function as well, because of derivation. Because I mean, we know that these vector fields are also derivation. It's a smooth section. Sorry, it's a smooth function, not a section. Function on U, and we denote it by just V of F. Okay. This construction is local because we know that derivations are local objects. So we don't really need to define it on functions defined on an open set, but we can define it directly on germs. So if F is a germ at the point P, and we have two vector fields, vector fields, oh my God, vector field defined in a neighborhood of P, then, well, we know that this V of F is a function, and vector fields can be applied to functions. So we can apply the vector field W to the function V of F at the point P, right? So F is a germ of a function. In particular, you take a representative in some neighborhood U, you apply V to it. Now this is again a function on the same neighborhood U. So we can apply another vector field, W, and then just compute everything at the point P. So this is well defined. Hence we can define a new vector field which is the Lie bracket of vector fields, which you've probably seen before, which at a point P acts simply just like we just said. For every F, which is a germ near P. Definition, VW is the Lie bracket. Of V and W. The bracket very important, lots of interesting properties. First of all, is the fact that something which a priori is not at all obvious, that this VW is itself a vector field. Yeah, not everything that acts on functions is necessarily a vector field. For instance, just taking one part of this, so just taking this is not a vector field. It acts on functions. You know, you can apply W composed V to F. But we know that when you do this, you get second derivatives, basically. But when you do it this way, all the second derivatives disappear. You get only first order. So you are, in fact, a vector field. But this is part of the exercise, which again is given as an exercise because I think you already know this. But if you don't, then do the exercise. Okay, when we have a vector field, we always have a thing called the flow of a vector field. So let's start with the tangent bundle 2R. This is a trivial bundle. It's just diffeomorphic to R times R. Yeah. But here we have a global section. Which takes S and sends it to the derivative with respect to the function evaluated at S. Yeah. So what does it mean? Well, it means that you take the derivative and you apply it to a function. Well, this is simply the derivative of that function. And you think of the function of t with respect to t, and then you evaluate it at t equal s. And f here is a germ of not function near s. Okay. So it's not simply the derivative, it's the derivative evaluated at the point. And here we have a theorem. If you take x, vector field on M manifold, then for every point in the manifold, there exists an epsilon and a neighborhood of P and the function. So this exists is for all these three things, an epsilon, a U, which is an open neighborhood of M, a neighborhood of P, and a map phi from minus epsilon times U in M, which is smooth, such that. So is that if you fix the, well, let's just immediately call it time component, you get the identity. If you take the derivative of this function with respect to the first component, yeah, at the point S, so with this I mean the derivative with respect to the first component evaluated S. So you know this is a differential, so we can apply it to a vector field, and we apply it to this vector field here. Then this is the same at X evaluated at the point. So we're not applying, oh yeah, maybe I didn't write it like this. This is evaluated at, it's not applied to. So evaluated at, it's like this. And this is for every S in this interval. Yeah, so let's maybe examine this a bit. You can think of as a map from S, like if you fix the thing here, this is a map from minus epsilon to M, right? So when you take the derivative, this is a map from T minus epsilon, which is not really TR, but it's very similar to TR. I mean, the section still exists in particular. So it's a map from T minus epsilon to T of M. So in particular, it's a linear map which sends vector fields to other vector fields. So all of this makes sense. And so this is an information about what happens with respect to the first one. Well, with respect to the second one, so if you fix the first coordinate, and you'll only look at this function of the second coordinates, this is a diffeomorphism. And sorry, this is for also a Q in you. For each fixed S in the interval. Okay. In particular, this thing here, you will never write it like this. So just for notation purposes, you will never write it like this. You will always write phi dot of Q. And maybe the S, you put it here. Okay, I mean, this is like the proper way to write it, but look at this. And this is very compact and nice. And okay, of course, we're not going to prove this, but the idea of proof is that in local charts, this is just a Cauchy problem. Yeah, it basically means you have like for every, you have an initial condition, and this is a differential equation. This part here is a differential equation because you're asking that some derivatives, like in local charts, is just a system of first order differential equations. Because you put everything in coordinates, and here you're like prescribing what these coordinates should be, and here you have the derivative with respect to time of these coordinates need to be something that is given. So it's just a Cauchy problem. And we know that for Cauchy problems, you always have a unique local solution. Yeah. So this is what happens locally, and then okay, you have to glue things, but this is just the idea. So now that we know that this thing exists and it's unique, because Cauchy. So given X a vector field, on M, then this map is the local flow of X at P. And P was the, P from before. And as I was saying before, we will always write phi t q for phi dq. Okay, so we really think about it. So we fix t and really think about it as a diffeomorphism of M. Yeah, so you can also think about this as a moving diffeomorphism. So as you vary t, you're changing the diffeomorphism. And for t equals 0, you have just identity. And we know that for flows, the semigroup law applies. So if you compose with this, you get the sum. Okay, for when it's defined, of course. When defined. Okay. Yeah, and as I was saying before, we will also write, we will write phi t dot q for derivative of phi qs. Yeah. So this is a vector field. Oh yeah, sorry, I have to apply it to this thing. So this is t and this is, okay, sorry. Here I should really use s. S t equal s. Okay. Yeah, so just think this is a vector field on M for fixed s. Okay, so this is still part of the recall. This is what the flow of a vector field is. So now let's recall another thing which is important, which is foliations. Have you ever heard about foliations? For bad news and without the O. For bad news theorem. Have you ever heard these two words?
I'm not quite sure whether
Okay, let's
I'll
see
have to
what it is,
translate
and
it.
then
Whether yeah.
and so okay, we start with the manifold of dimension n. Dimension n. A foliation. We usually denote it by cursive f of dimension m, which must be strictly smaller than n, is given by an atlas u alpha phi alpha of m, such that if you look at it into Rm times Rn minus m, satisfies that if you have two charts which intersect, then the change of coordinates, so phi alpha composed phi beta inverse x, y, is of the form h alpha beta xy, comma g alpha beta. And this part, it's only dependent on the second n minus m coordinates. These are m, sorry. Okay, it's in Rm times Rm minus n. Yeah, it's this division is the same as this division. Okay. So basically you have that n minus m coordinates kind of live by themselves. They still influence the other m, careful, yeah, because here you do have a y. But otherwise they kind of live by themselves. Definition, the connected components, of L alpha y0, which is defined as the anti-image with respect to alpha, the phi alpha, sorry, of Rm times y0 intersected, of course, the image of phi alpha, u alpha. Yeah, so basically I'm just saying that, okay, look at the local chart and just take a slice Rm times y0. So m dimensional slice and send it back to the manifold M. Yeah, are called plugs. Okay, so in local chart, this is just the single slices. You have this Rm, you have just think of R times R. You have these two things, and you have the slices, and just send them back. These are the plugs. And observe that you have that basically two plugs in different charts are the same. Okay, I cannot talk about this, right? Because they can never be the same because one lives on U alpha, one lives on U beta. But if I intersect with the opposing one, so these both live on U alpha intersected U beta, if and only if, yeah, I think so. G alpha beta of y0 prime is the same as y0. So for sure, remember that these G alpha betas, these are not transition functions of a bundle, yeah? So these are not matrix things. These are the transition functions of a manifold. Okay, so they're simply diffeomorphism from, well, in this case, from Rn minus m to Rn minus m. Okay. And yeah, so you have a plaque that lives in U alpha, you have another plaque that lives in U beta. When are they touching each other, basically, on the intersection? Well, only if the point, sorry, this is not an if and only if, this is just one direction. If the point is like the same point in the manifold, basically, yeah? Because remember, y0 is in the trivialization and y0 prime is in the trivialization. So asking this condition here is like saying that when you look at them in the manifold, not in trivialization anymore, they are the same point, really. But only with respect to this second part. Okay. So now that we know when two plaques are like gluing together, we can define the notion of leaves of a foliation. We say that two points are the same if there exist plaques P1, Pk, such that X is in P1, Y is in Pk. Successive plaques have non-empty intersection. And so basically you're saying that two points are equivalent if there is like a path of plaques between them. And equivalence classes are called leaves of the foliation. Okay. So this is all this usual very abstract definitions, which maybe don't tell you a lot if you've never seen these things before. So let's give a proposition which kind of gives a better idea of what these foliations are. So you have a map F from M to N. If it is a submersion, so surjective differential at every point, then M as a foliation with leaves F equal C, where C is in N. N the manifold, not natural numbers. Okay. So basically the idea of a foliation is that you have this manifold M and you're slicing it with M dimensional submanifolds. That's basically what you're saying. And in a chart, this is done by Plex. So what's the easiest way to slice Rn in M dimensional submanifolds? Well, just take M dimensional planes. Yeah, just take M dimensional planes and just cover everything. And they're disjoint and blah, blah, blah. And here, okay, locally, this is the picture. And then you kind of glue a lot of these pictures together. And this condition on the definition of a foliation, so this part here, it ensures you that if here you have slices and here you have slices, the slices glue together. Yeah, like every plaque can only intersect one other plaque in a different chart if this is simply connected. Blah, blah, blah. Okay, so this is the most standard way because when we have a submersion, each one of this is a submanifold of dimension equal to dimension on M minus dimension of N. Yeah, it's co-dimension dimension of N. And by the this is a bit stronger by the adapted submanifold charts, because the adapted chart for a submanifolds only tell you that that particular submanifold is in a local chart is the 0 set. This is a bit stronger because it's telling you that this one is the 0 set and the next one is the 1 set and the next one is the 2 set and blah blah blah. But even better, in a continuous way, it's not discrete. Like each one of them is one particular level set in a chart. So this is stronger. Okay, how does this relate to what we're doing? If you have a manifold, a distribution V on M of rank R is a subbundle of the M of rank R. So this is what we call a distribution. And if we have a foliation, then there exists a unique distribution V such that if you look at this distribution over a point, this is precisely the tangent space to one of the leaves. Leaf of F passing through B. Okay, so the theory is simple. You have this foliation. So for every point, you have a submanifold of dimension M, and you just take the tangent space to that manifold. And this is automatically subbundle of M of dimension of rank R, where R is the dimension of these leaves. And yeah, so this gives you a distribution because you have this subbundle and a subbundle of rank R. So now the question is the inverse. So I have a subbundle of rank R, so I have a distribution of rank R. Do I have an associated foliation? And the answer is not always. So definition, distribution V is integrable if and only if for every two vector fields in this distribution, so meaning that over every point you are in the, so these are sections of V. Also, their Lie bracket is in V. Theorem, THM theorem, Frobenius. This is the so-called Frobenius theorem. V distribution. Oh, sorry, my bad. I mixed two definitions. So distribution is integrable when that thing happens. So it's integrable when there exists a foliation. So if by definition there exists a foliation such that VP is TPL for every P in M. So this division of integrable. So so we know that if you have a foliation, then you have a distribution. But if I have a distribution, do I have a foliation? If it's true, then we see the distribution is integrable. Then you have another definition for a distribution. Distribution V is involutive if, only if, for every V and W in V, also V W is in V. Okay, and okay, one direction, since it's obvious. So if you have something that is integrable, then this is automatically involutive. Why? Because remember that if you're integrable, you're basically just a tangent space. At every point, you're a tangent space. So you can think of that's just the tangent space of a manifold. So if you have a vector field on a manifold and another vector field on a manifold, the Lie bracket is again a vector field on that manifold. So this gives involutivity. The theorem from Frobenius is that a distribution is involutive if and only if it's integral. So one direction is obvious, but you have this other direction. So if you have this condition that in fact every time you take two vector fields in the distribution, the Lie bracket is again in the distribution, then you can actually cook up this foliation, which has this precisely as its tangent space. Okay, so the theory of foliation, it's huge, and you've never seen this theorem before, this word involutive integrable. Oh, interesting. Okay. I'm pretty sure we'll not use it too much, but it's something that is like good to know. And yeah. Okay, so I think this concludes today's lecture, and I will see you tomorrow.